Hello and welcome to today's lesson, linear regression hypothesis testing. So in our last lesson, we saw how to build a confidence interval for linear regression models. Okay, today we're going to be looking at constructing a hypothesis test for a linear regression model. So our objective for today, by the end of this lesson, I will understand how to construct a linear regression hypothesis test and why they are important in statistics. So the question of why. Once again, linear regression lines, a common way to create prediction models for two variable data. Okay, since the models are not perfect, we can use the hypothesis test to determine if there is a relationship between the two variables or is there a no relationship situation. So this is kind of, connected to the correlation situation. Is it a strong positive relationship? Is it a positive relationship between the two variables, or a no relationship or negative relationship between the two variables? So we're going right back to our example that we had in the confidence interval lesson. We've got the 12 members of the college women's golf team. We've got their first round, second round scores, and we're making a prediction model of can the first round score predict the second round score. Okay, so once again, we've got our two models here that give us the values that we're looking for. Okay, we have the calculator output from a TI-84 for the linear regression, and then we can see the computer output. So we can see the same values here. Remember, we've got A and B going down for the coefficients. Okay, standard error S of B1. Okay, we'll see this again here. We talked about it in that last lesson as well. We've got our R squared value here. We can see that matches with what we have from the graphing calculator. And then when we're dealing with two variable data, our degrees of freedom is always n minus 2 because we have two unknown variables. The slope is truly an unknown variable, and the y-intercept is an unknown variable. And remember what the y-intercept means. The y-intercept is the score from round 2 if the round 1 score is 0. Now we know in this situation, it's pretty much impossible to get a score of 0 in a round of golf, but we always look at that linear equation and want to make sure that we can understand the two variables that are given to us for a regression line. Okay, assumptions. Okay, we've got our basic assumptions again. Okay, we're looking back at our graphs that we have. Okay, we've got a few pieces that we want to look at here. Okay, and that's why this one's a little more tedious in some ways because of the number of graphs you need overall. So when we're looking at our assumptions, we've got our three normal assumptions that we've had in every situation: random, independent, and normal sampling distribution. Okay, so we have those as well. Okay, for these purposes, both random and independent are covered by your simple random sample. Okay, so if you're doing a simple random sample, one, we know it's random. But when we're talking about individual points, a randomly sampled point is independent of any other randomly sampled point. So now our normal distribution, okay, it's not actually a linear process of what we do, but when we try to prove something to be normal, okay, just like we had back in the mean value, we have to do a box and whisker, but this is a box and whisker on the residual values. So you have to do a residual plot, which you'll need to prove our last assumption, linearity. Okay, but once you have your residual values, you have to do a box and whisker so we can prove that it's normal. And all we're looking for is to making sure that there's not extreme skew, which there is no extreme skew in this situation, slightly skewed to the right, okay, but very slightly skewed to the right. So this is an approximately normal sampling distribution of residual values. But to prove linearity, just like we had in our last unit, linear regression, when we're trying to prove linearity, we need to show the original data plot. Okay, least squares regression line is helpful to include that as a part of this graph. And then we need the residual plot. Remember, the residual plot is the #1 way you can prove if a linear regression model is the proper model instead of a nonlinear model. Okay, so those are our 4 assumptions for doing confidence intervals or hypothesis tests with linear regression data. Okay, so now hypotheses. When we're looking at hypotheses, #1, we always have to go back to a population value beta. Okay, beta is represented by the b value of the slope. Okay, make sure that you define what beta is. Okay, beta is the true slope of the least squares regression line comparing all of the round 1, round 2 scores for this women's college team. And then you have your alternative hypothesis. Okay, notice we're always comparing to 0. Okay, 0 for us means that there is no relationship between the two, a slope of 0. And know that in a very rare case, we could change this to 1 if we're looking for a perfect relationship between these two variables. But we have our typical alternatives: greater than, less than, not equal to, okay, all based on what's stated in the question. Okay, you have to make sure that you take your information from the question to set up your problem. So now, our calculations. Okay, we need to build a test statistic. In this case, our test statistic is t because we're using the sample to estimate a standard deviation. Okay, whenever we use the sample to estimate a standard deviation, just like our mean value problems, we have to use a t-value instead of a excuse me, normal distribution or z-value. Okay, now remember, standard deviation of B1, okay, a pretty nasty formula for calculating that. Okay, we've got the standard deviation of the residual values is this top portion of the formula, and then we have a sum of the x value distance squared. Okay, so you can see how this is really truly kind of a slope value. Okay, you've got residual distance, your y, which is on top of the slope, and then you have the x value distance compared to average in the denominator of that value. Okay, so now how do we build our t statistic? Okay, to build t, remember we need a, b, and then s of b1. You know, this top one would be s of a1 if we need that standard error of the y-intercept, but that's not something that we use very often. Okay, calculating our t-value. Okay, we've got our given b, 6.88, minus beta. Okay, that goes back to your null and alternative value like any other hypothesis test, divided by the standard error of b. Okay, so we run that through the calculator and we get 2.99, okay, which is nice. The computer printout, if wanted, gives you that t-value for the distribution. Okay, now remember, for full credit, we need to show the calculation for t, and then we also need our probability statement. What's the probability of t? And in this situation, I'm just going to be going with a greater than value, 2.99. Okay, so now we would go to the calculator. Remember, in our distributions, okay, we're going back to t-values. We haven't worked with them for a little while, but we've got the t-CDF. Lower boundary, 2.99. Upper boundary, positive infinity, or 10 to the 10. And then we have our degrees of freedom of 10. Sample size minus 2. Okay, so we paste that in, and we hit enter. Okay, we get a probability value of 0.0068. Okay, now, if you notice, okay, it doesn't match this probability here. Okay, why doesn't that probability match with what we have? The probability that's given to you in the table is for a not equal to hypothesis test. So if you notice, if we double this value, okay, we are going to get almost exactly what we see there. Okay, so know that when you're given that probability in the table, it's for a two-tail hypothesis test or a not equal to, and in this case, I ran a greater than test for this one. Okay, and then finishing up. Okay, same finish for every hypothesis test, no matter what the situation. State your evidence that leads you to your conclusion about the null. And then once you've made a conclusion about the null, you're going to make a statement about the alternative in context. So here's our conclusion down here based on our evidence. P-value of 0.0067, 0068, less than our 0.05 significance level. We reject the null hypothesis. This evidence supports the alternative hypothesis, which states that the slope of the least squares regression line comparing round 1 and round 2 golf scores is greater than 0. Okay, so for extra practice on this, besides your Schoology quiz, we've got the in-class packet problems, and all you want to do is finish the packet. Remember, in our last lesson, talking about confidence intervals, we went through the majority of the in-class extra practice packet, and then here you're just going to be finishing up the 2 pieces that have you deal with significance tests or hypothesis tests. Thank you, and have a good day.